How do you heat a 102-story building in 1930 when conventional radiators and boiler pressure could only push steam up about 6 floors? That was the impossible math facing the engineers behind the Empire State Building. 1,250 feet of tower, 6,514 windows bleeding heat into 25-degree New York winters, and a demand of 35 million BTUs every hour. One miscalculation, and the tallest building on Earth becomes an uninhabitable frozen column of steel and limestone. The answer required rethinking everything engineers believed about steam. The Empire State Building stands as a monument to ambition, 1,250 feet of steel and stone, stretching so high it seems to ignore the rules that govern ordinary buildings. In the depths of a New York winter, with the mercury stuck at 25 degrees Fahrenheit, this tower faces a challenge that most people never consider: how to keep every corner warm, from the crowded lobby to the wind-battered observation deck a quarter-mile above the street. The problem wasn't just about making people comfortable, it was about survival for the building itself. Stone, steel, and glass all leak heat, and with 6,514 windows, the Empire State bleeds warmth into the frozen air at a rate that would overwhelm anything less than a small power plant. The numbers are staggering: over 2 million square feet of floor, more than 1.5 million square feet of exposed exterior, and a heat demand that can spike to 35 million BTUs per hour during the coldest nights. That's enough energy to heat a small town, delivered vertically through the heart of the tallest structure on Earth. But the real puzzle wasn't just about scale, it was about physics. Early 20th century steam heating systems had a hard ceiling. Steam pressure could only lift heat up about 6 stories before gravity and pipe friction brought everything to a halt. That was the industry's rule. No matter how much steam you produced, it simply couldn't rise high enough to warm the upper floors of a true skyscraper. Any attempt to push steam further risked stalling the system, flooding radiators, or worse, leaving entire sections of the building cold and uninhabitable. Yet the Empire State had to defy that 6-floor rule, not just once, but 17 times over. Every winter, as wind whipped around the limestone and aluminum facade, the building's hidden infrastructure was tested to its limits. The task was relentless: keep a vertical city warm, with nothing but the technology of the 1930s and the laws of steam physics. The solution would have to be as bold and original as the building itself. Heat loss in a giant like the Empire State Building is a numbers game on a scale few buildings ever face. The tower's envelope, walls, windows, roof, spans over 1.5 million square feet exposed to the elements. Add in the floors, and the total interior area stretches to 2.2 million square feet. Every square foot acts as a pathway for heat to escape, especially when New York shivers at 25 degrees Fahrenheit outside, and the goal is a steady 70 degrees inside. The building's 6,514 windows, each set in limestone and steel, offer stunning views but also leak warmth at a relentless rate. Engineers in 1931 calculated the heat loss using a U value of about 0.5 BTU per hour per square foot per degree. Fahrenheit, a typical figure for the era's steel-framed masonry. With a 45-degree temperature difference from inside to out, the walls and windows alone bleed away nearly 30 million BTUs per hour. That's before accounting for cold air sneaking in around doorways, elevator shafts, and the constant churn of people coming and going. Lighting, office equipment, and the sheer number of bodies inside add a small amount of heat, but not nearly enough to offset the losses. During the worst winter nights, the building's total demand can spike to 35 million BTUs per hour. To put that in perspective, it's the equivalent energy needed to heat more than 1,000 average homes at once. The sheer volume of heated space, the vast surface area, and the thousands of windows all combine to create a heat load that rivals a small industrial plant. For the Empire State, this wasn't just an engineering curiosity, it was a daily operational reality. Every hour, the heating system had to replace the energy lost through glass and stone, or the upper floors would quickly grow as cold as the city outside. The numbers alone made clear that ordinary solutions would never be enough. The building demanded a heating system as ambitious as its architecture, and the math set the stage for the next engineering challenge: how to move that much heat vertically against the limits of steam itself. Low-pressure steam heating, the workhorse of early 20th century buildings, runs into a hard wall when faced with the vertical reach of a skyscraper. The problem starts with hydrostatic head. For every foot you try to push water up, the weight of the liquid pushes back with 0.433 pounds per square inch. At the standard 2 pounds per square inch supply pressure used in most steam systems, that means you can only lift condensate about 4.6 feet before gravity wins. In practice, with floor heights around 11 feet, that sets a ceiling at 6 stories. Any higher, and the pressure at the top isn't enough to keep water moving back toward the boiler. But hydrostatic head isn't the only enemy. As steam travels up and through the maze of pipes, it loses pressure to friction, roughly 1 ounce for every 100 feet. In a building like the Empire State, with vertical runs stretching hundreds of feet, the cumulative friction loss chews up what little pressure is left. By the time steam reaches the upper radiators, there may be nothing left to drive the flow or return the water. This is why, for decades, the industry's 6-floor rule was ironclad. Try to serve more floors in a single loop, and you risk disaster. Radiators starved for steam, pipes filling with water, and the constant threat of water hammer. The only way to keep the system working was to let gravity return the condensate. But gravity alone can't fight the pressure head in a tall building. The Empire State's engineers faced a simple but brutal arithmetic. A 66-foot height produces a hydrostatic head of about 28 pounds per square inch, far beyond the 2 pounds per square inch available. No amount of clever pipe routing or oversizing could change the basic physics. The 6-story limit wasn't just a design guideline. It was a law written by pressure, gravity, and friction. Solving this would require a completely different approach, one that reimagined how heat could be delivered, collected, and sent back down in a vertical world. Steam heating in a low-rise building is simple. A single boiler pushes steam up through vertical risers, feeding radiators on each floor. Gravity brings the condensed water back down to the boiler. But in a skyscraper, gravity becomes the enemy. The pressure required to lift water up even a few stories quickly overwhelms the modest 2 psi that most radiators can handle. In the Empire State Building, every 6 floors add nearly 3 psi of hydrostatic head, more than enough to stall a gravity return and leave the upper floors cold. The solution was vertical zoning. Rather than forcing steam to climb the entire height of the tower in a single loop, engineers divided the building into a series of stacked pressure zones. Each zone was essentially a self-contained heating system, stretching no more than 6 stories high. At the heart of each zone stood a riser, a vertical pipe that delivered steam from the main supply. At the base of each riser, a pressure-reducing valve, or PRV, stepped down the incoming steam to the gentle 2 psi needed for safe radiator operation. This careful control kept each zone within the pressure limits that allowed both steam delivery and reliable condensate return. The building's mechanical floors acted as the backbone of this system. 4 major mechanical levels spaced strategically up the tower housed the PRV-S vacuum pumps and control panels that managed each zone. The main risers, thick insulated pipes up to 8 inches in diameter, ran vertically from the sub-basement to these mechanical hubs. At each floor, branch pipes split off, feeding radiators across that particular zone. The result was a series of 6-floor stacks, each one isolated from the next by its own set of valves and controls. This approach solved the pressure problem by breaking the building's 102 stories into manageable segments. Within each zone, the steam only needed to travel up about 66 feet, well within the limits set by gravity and friction. The pressure at the top radiator in a zone never dropped below what was needed for heat to flow and for water to return. By resetting the pressure at each mechanical floor, the system could deliver consistent warmth from the lobby to the uppermost offices, no matter how fierce the wind outside. Each zone operated almost like a mini-building within the larger structure. If a valve failed or a leak developed, engineers could isolate the affected zone without shutting down heat to the entire tower. This not only improved reliability but also made maintenance safer and more practical. Redundant pumps and manual isolation shutters mean that even a serious failure would not leave the building freezing. The real genius lay in how these zones worked together. Steam entered the building at much higher pressure, up to 30 psi, direct from the city's district steam network. It was then stepped down, zone by zone, until it reached the familiar 2 psi used by the radiators. Each riser and PRV formed a link in a chain, transforming what could have been a single, unmanageable vertical leap into a series of controlled ascents. The pressure zones became the hidden architecture that made the Empire State Building's heating system possible, turning a skyscraper into a stack of livable, warm spaces, each one protected from the harshest winter by a carefully balanced loop of steam and steel. Beneath the Empire State Building, winter heat began with the thunder of steam and the discipline of engineering. The Empire State Heating Company's basement machine room was a world apart, its concrete walls echoing with the hiss of valves and the steady pulse of city steam. At its core stood a 6-inch steel service valve trimmed for safety, linking the building to Consolidated Edison's district network. This valve, rated at 225 psi, was built to withstand far more than the pressures found above, ready to admit a surge of saturated steam from the city's labyrinth of underground mains. The city's network ran hot, often pushing steam at 150 psi through miles of pipe. When it reached the Empire State sub-basement, the force was enough to supply a vertical city. The valve station, designed for swift isolation, could cut the building off from the city main in seconds, a safeguard against leaks and emergencies that could threaten everything above. Standing by, 4 water tube boilers, each capable of producing 18,000 pounds of steam per hour, waited in reserve. Their coal hoppers were fed by a rail spur that vanished beneath 34th Street, a reminder of the building's appetite for energy. These boilers rarely ran at full tilt. Most days, Con Edison's supply was enough. But when demand spiked or the city's line faltered, the on-site plant roared to life. The air thickened with coal dust and the scent of hot iron, and the boiler crew, stationary engineers in leather aprons, watched the gauges, knowing a single mistake could echo through the tower. Steam entered at pressures that would destroy ordinary radiators. The first task was to tame it. Pressure-reducing valves, arranged in parallel for redundancy, stepped the pressure down from city levels to about 30 psi, still high but manageable for the building's risers. Each PRV could handle up to 2 million pounds of steam per hour, more than double the building's peak winter load. This margin allowed for future growth and the unpredictable swings of a city that never slept. From the valve room, steam surged into a central riser, a 5-inch steel pipe wrapped in mineral wool, bracketed at every floor. This unseen artery fed energy to every zone, while a separate return line carried spent condensate back to the basement for cooling, filtering, and discharge or return to the city network. The basement was more than machinery. It was a living system, tended by engineers and firemen working in shifts, their logs recording the rhythm of pressure and emergency. Here, the city's invisible infrastructure became personal responsibility. The roar of steam and the vigilance of its operators formed the foundation for everything above, turning ambition into warmth and light. At the heart of the Empire State Building's heating system runs a vertical artery that few ever notice, the main steam riser. This pipe, 5 inches across and sheathed in 4 inches of mineral wool, climbs nearly 800 feet from the sub-basement to the uppermost mechanical floors. Its path is hidden behind walls, bracketed to the building's steel skeleton at every level. But its mission is simple: carry enough heat in the form of pressurized steam to serve a vertical city in winter. The riser's size and insulation weren't chosen at random. Engineers knew that steam, if left unprotected, would lose precious energy to the cold core of the building. Mineral wool lagging, layered thick around the steel, cut heat loss to less than 10% along the riser's length, a critical margin when every BTU counts. To keep the system quiet and reliable, the steam velocity inside the riser was carefully limited to under 15 feet per second. Any faster, and the flow would roar or erode the pipe from within. Any slower, and the system could stall under peak load. The scale of the riser is a direct answer to the building's demands. On a freezing January night, the riser must deliver nearly 1,800 pounds of steam per hour, enough to keep 2.2 million square feet of space at a steady 70 degrees. The pressure at the base, stepped down from the city's district steam, enters at about 30 pounds per square inch, far above what radiators can handle, but necessary to drive steam upward against friction and gravity. As the riser climbs, it feeds each zone through a series of branch manifolds. At every mechanical floor, pressure-reducing valves tap the main, carving the building into manageable steam territories. Every inch of the riser's length is a balancing act. Too narrow, and friction would sap pressure before the steam reached the highest floors. Too wide, and the cost and complexity would spiral. The pipe's diameter, the thickness of its insulation, and the velocity of the steam all reflect a careful compromise, one that allows the riser to act as a highway for heat, not just a conduit. Over decades, this hidden backbone has endured, quietly channeling energy from the city's grid into the bones of the Empire State, floor by floor, winter after winter. Behind the limestone and glass, the Empire State Building's mechanical floors form a hidden network that controls the building's entire heating system. These aren't just utility spaces, they're layered hubs, each with a distinct role in managing the immense flow of steam from New York's district mains. At the lowest level, B2, steam enters the building at pressures up to 150 pounds per square inch. The main service valve and the first pressure-reducing valve, or PRV, are stationed here. This cast-iron diaphragm unit drops the pressure to about 30 pounds per square inch, a level still too high for radiators, but perfect for sending steam up the main riser without losing force to friction or gravity. Above B2, M1 sits 38 feet higher and acts as the first major checkpoint. Here, another PRV further reduces pressure, and the original Nash vacuum pump begins its work. The Nash pump pulls a partial vacuum, about 4 inches of mercury, helping draw condensate back from the upper floors. M1 also houses condensate collection tanks and control panels, giving engineers real-time oversight of flow and pressure. Each PRV is pilot-operated, with adjustable orifice plates that let staff fine-tune output for changing weather or building loads. M2 and M3, at 71 and 86 feet above B2, each host their own PRVs and auxiliary condensate pumps. These stations break the building into smaller pressure zones, ensuring steam never climbs more than 6 floors before being reset to the gentle 2 pounds per square inch needed for radiator safety. Relief valves set to 30 pounds per square inch stand guard at every hub, ready to vent excess pressure if something goes wrong, a safeguard that has prevented disaster more than once. Each mechanical floor is lined with steam trap assemblies, about 50 per zone, which keep water hammer at bay and protect the delicate balance of flow and return. Engineers and maintenance crews walk these narrow aisles, checking gauges and listening for the hiss or rattle that signals trouble. Their vigilance keeps the system running through winter storms. Without these stacked control centers, the Empire State would be just another cold, uninhabitable tower. Instead, it remains a vertical city, its comfort and safety guarded by a network of hidden hubs, each one a small fortress of valves, pumps, and human ingenuity. Beneath the Empire State Building's marble floors, a quiet machine solved a problem that had challenged engineers since the dawn of skyscrapers. The Nash liquid ring vacuum pump, designed by Lewis H. Nash in the early 1900s, was installed in 1931 as the backbone of the building's heating system. The task was deceptively simple: return thousands of pounds of condensed steam, now hot water, from radiators as high as 1,250 feet above the street. Gravity alone couldn't do it. After 6 stories, the pressure difference just wasn't enough. Without a way to pull this condensate home, radiators would run cold and pipes could burst from trapped water. The Nash pump changed the equation. By drawing air from the return lines, it created a vacuum, about 4 inches of mercury, or nearly 2 pounds per square inch below atmospheric pressure. This negative pressure was enough to pull water down from the highest radiators, overcoming the hydrostatic head that would otherwise defeat the system. The original CL-1002 model, tucked into the sub-basement, could move up to 2 million pounds of condensate per hour, far more than the building's peak demand. Its liquid ring spun at high speed, using water to form a seal and generate suction, a design that handled grit and constant cycling with remarkable reliability. For over 80 years, the Nash pump quietly kept the Empire State warm through winter storms and blackout nights. In 2014, engineers installed a modern upgrade: 2 10-horsepower liquid ring pumps, each able to move 3,000 pounds of condensate per hour under a sustained 4-inch vacuum. This dual arrangement ensures redundancy. If one fails, the other keeps the system running. The logic remains unchanged. Condensate from every floor, from the 6th to the 102nd, is drawn back to the basement, closing the hydraulic loop and allowing the heating cycle to run without interruption. The Nash vacuum didn't just move water, it allowed the entire building to function as a single, interconnected system. By lowering the pressure needed for return, engineers could divide the skyscraper into manageable zones, all heated by low-pressure steam. The hum of the Nash pump became the heartbeat of the Empire State's hidden engine room, a testament to physics and ingenuity that kept a vertical city alive through generations. Steel and steam rose together, locked in a race against the clock. As the Empire State Building's skeleton climbed skyward at nearly 4.5 stories per week, the installation of its heat system became a feat of choreography. Pipe fitters and riveters worked shoulder to shoulder with iron workers, threading 5-inch steam risers through the heart of the building as soon as each floor's steel frame was set. Each riser section arrived pre-cut and insulated, ready to be hoisted through narrow shafts on a custom rail system that snaked up the central core. Crews had just 2 minutes, the gap between a floor's steel placement and the next concrete pour, to bolt, align, and weld each length of pipe into place. Miss that window, and the schedule would slip, threatening the entire project's momentum. A team of 4 riveters per floor kept the pace, working in a blur of heat and hammer blows. While one crew secured pipe brackets to the steel columns, another spliced riser joints and checked for perfect alignment. The process ran like a relay. As soon as the steel advanced, the pipe crew followed. Then the concrete gang sealed it all in. This relentless rhythm, floor after floor, day after day, allowed the building's mechanical backbone to keep up with the fastest skyscraper construction ever attempted. By the time the frame topped out, the main steam risers were already in place, ready to channel heat from the basement to the highest occupied floors. The result was not just a marvel of speed, but a display of tight coordination, an invisible infrastructure rising in lockstep with the tower itself. John Rogers stands at the heart of the Empire State Building's hidden machine. His shift begins in the pre-dawn chill, deep in the sub-basement where the city's steam supply enters the building. Rogers, a stationary engineer with 20 years on the job, moves between rows of brass-rimmed gauges, clipboard in hand. He reads the steam pressure, 1.8 pounds per square inch on the supply line, steady as a drum, and glances at the vacuum return, holding at 3.9 inches of mercury. These numbers are more than routine. They are the pulse of the building, and Rogers knows them by feel as much as sight. The room is never silent. There's the low hiss from a pressure-reducing valve, the hum of the Nash vacuum pump, the faint clatter of tools as the maintenance crew checks a flange or lubricates a valve stem. Rogers logs every reading, every shift in the needle, in a ledger that stretches back decades. His notes are plain: 1.8 pounds per square inch supply, 3.9 inches of mercury vacuum, no deviation. But behind each entry is vigilance. A sudden drop could mean a steam trap is stuck open. A spike might signal a blockage in a riser. The system is designed for redundancy, but the first line of defense is always a human eye on the gauges. On a typical winter morning, Rogers and his team walk the mechanical floors, checking for the telltale sound of water hammer or the faint scent of overheated insulation. The building's comfort depends on their attention. It's a job that demands patience, routine, and a kind of quiet pride. The machinery may be monumental, but the difference between warmth and cold often comes down to one person, reading the numbers right when it matters most. December 1932 brought a scare that could have changed everything. On a weekday morning, a pressure-reducing valve on the 71-foot mechanical level jammed open. Steam surged through the zone, and within seconds, the gauges jumped from their usual 2 pounds per square inch to 4 pounds per square inch. This spike was strong enough to threaten every joint and radiator in that segment. The engineers on duty moved fast. One sprinted to the manual relief valve, venting the excess before the pressure could climb higher. Another isolated the affected zone, shutting off the faulty line while the rest of the building stayed warm. A post-mortem in the maintenance log revealed the culprit. The pilot diaphragm inside the PRV had torn, unable to hold against the sudden force. The team did not just swap in a replacement. They installed a new diaphragm made from hardened steel, a material chosen to resist fatigue and last through decades of cycling. This single upgrade set a new standard for every PRV in the building. The engineers also tested the isolation protocol, confirming that any zone could be separated in seconds, no matter the hour or weather. After that morning, the building's crew treated every pressure reading with fresh respect. They walked the mechanical floors with a sharper eye, knowing that the system's strength lay not just in its pipes and valves, but in the people who watched over them. The Empire State's heating system had faced its first real crisis and come through intact, its resilience forged by a blend of quick thinking and hard-won engineering lessons. Blueprints for new skyscrapers in the decades after 1931 often included a familiar diagram: vertical pressure zones, mechanical floors stacked like vertebrae, and a vacuum-assisted condensate return. The Empire State Building's heating system didn't just solve its own winter problem, it became the template for towers rising across American cities. Engineering memoranda from projects like the Prudential Tower in Boston and the Bank of America building in San Francisco reference the Empire State's zone-by-zone approach. Designers cited the same six-floor rule, the same pressure-reducing valves, and the same Nash liquid ring vacuum pump that had proven itself in New York's most demanding test case. Trade journals in the 1930s and 1940s dissected the Empire State's method, urging mechanical engineers to adopt vertical zoning and vacuum return as standard practice for any building rising above 10 stories. The argument was simple. If a two-PSI system, segmented and assisted by vacuum, could keep 102 stories warm, it could work almost anywhere. Copies of mechanical blueprints circulated among engineers, annotated with notes on pressure drops, pipe diameters, and safety margins. The cascade of imitation was swift. By 1955, the Prudential Tower's design documents explicitly referenced the Empire State's pressure stepping and vacuum system as the backbone of its own heating strategy. The solution that once seemed tailored to a single impossible building became the foundation for an entire generation of high-rise climate control, each new tower borrowing from the hidden logic first mapped out in the heart of Manhattan. Tucked behind marble, steel, and glass, the Empire State Building's true artistry is almost never seen. Steam risers, vacuum pumps, and pressure valves, each one shaped, placed, and tested by hands that understood both the limits of physics and the promise of ambition. The public marvels at the skyline, but it's the hidden work, the hours spent threading pipe through narrow shafts and tuning valves in the half-light of the basement, that keeps the winter at bay. Every bracket and weld, every insulated joint, carries the legacy of craftsmen who built not just for the moment, but for decades of storms and silent nights. This is a building where elegance and utility are inseparable. The same Art Deco lines that draw the eye upward also conceal a lattice of mechanical genius. In the hush of a mechanical floor, the hum of a Nash vacuum pump is as much a part of the building's life as the spire that pierces the clouds. The engineers and crews who walk these hidden corridors know their work will never be celebrated in guidebooks, but their vigilance is what makes the tower more than stone and steel. Some of the greatest achievements are measured not in height or fame, but in the quiet confidence that, no matter how cold the night, warmth will rise, unseen, through the bones of a city's most iconic landmark. To this day, the Empire State Building's 102 stories depend on an intricate living system, engineered zones, relentless pressure checks, and the vigilance of maintenance crews in the unseen depths. Modern skyscrapers still echo these solutions, proof that invisible ingenuity shapes our cityscapes as much as steel and stone. Every warm office above Midtown owes its comfort to a legacy of calculated risk and human craft. The real marvel is not just what we see, but what endures behind the walls.